To construct a pyramid, it's necessary first to choose a suitable location and establish an infrastructure. On the Giza Plateau overlooking the Nile Valley, the Egyptians find an ideal location, quite large, gently sloping, and with limestone in abundance. They start to build the infrastructures there. They have to establish lines of communication and transportation for the stone. They dig the necessary canals to transport the stone, including Tura limestone, extracted from the east bank of the Nile, and Aswan granite, quarried 900 kilometers south of Giza. There they have to house the workers. There will be about 4,000 people working permanently on the site. First, there are the construction professionals, architects, foremen, masons, carpenters, and other qualified workers. There are also the seasonal workers, for example the peasants who come to carry out a sort of pyramid duty while their fields are inundated by the flooding of the Nile. Assigned simple tasks like handling materials, they're paid in kind, food and drink, and earn their place in eternity in contributing to the building of their king's eternal monument. Finally, there are the ancillary services and all their trades, toolmakers and repairers, butchers, bakers, fishmongers. Contrary to later popular belief, there are no slaves. Constructing the pyramid is an enterprise that is both religious and social. It is the big state project that unites Upper and Lower Egypt in one common venture. Besides the canals and the towns, 2 ports are required. A commercial port for the ancillary services and a port to receive the construction materials, which we're flying over now. And here are the red granite beams from Aswan. The Egyptians extract them by striking the stone with balls of dolerite, a material much harder than granite. This is very long and very painful work. These beams were ordered right at the start of construction and will not be installed until 14 years later. Extraordinary proof of anticipation and planning. You can see now the limestone rafters from Tura that will top various chambers in the pyramid. This very beautiful, fine white limestone will also be used for encasing the monument. And right here are the limestone blocks from Tura, which would form the skin of the pyramid. This limestone had a special characteristic. It was very soft in the quarry, but hardened quickly on contact with the air once mined. Therefore they had to cut the soft stones immediately to their final form, complete with beveling. These casing stones were then numbered and shipped to the work site, a perfect example of prefabrication. We look back on the 5th year of construction, which also corresponds to the 5th year of Khufu's reign. The materials that had arrived at the port would now be transported along a wide causeway leading to the work site that we can see in the distance. The causeway, which we will call the port ramp, had a gentle slope of about 8% and ample width, enough for the massive supplies required for the work site. Following the topography of the plateau, it ran judiciously through the middle of other quarries, providing limestone that was of a lesser grade than that from Tura, but was abundant on the plateau. They would supply the major part of the materials for the pyramid. Here in red, we see the route taken by the granite beams. In mauve, the route used to transport the limestone, extracted from these quarries that are starting to be exploited, and in white, the route used for the limestone supplies from Tura. You see that the quarrymen were working on smooth surface stones and more crudely cut stones at the same time. We will soon see why. The stones were transported on wooden sleds, an example of which can be seen in the Cairo Museum. The blocks of local limestone would then be pulled up a second external ramp, which we'll call the pyramid ramp. About 325 meters long, with a slope of 8%, it was built with the same limestone taken from the local quarries. This ramp had 2 lanes, one to allow the stones to be transported, the other in the process of being raised in height. The pyramid was constructed in successive horizontal layers called courses. During the construction of one course, the ramp was elevated to prepare for the construction of the next course. In this manner, construction never stopped, the ramp and the pyramids progressing together. As for the Tura limestone blocks intended for the outer casing, they followed a very different route. They were transported via an internal ramp, also with a gentle slope, constructed behind the pyramid's surface, starting from its base. Here we can see the entrance. This internal ramp constitutes the principal idea behind Jean-Pierre Houdin's theory, the construction of the pyramid from the inside. This is the principle. The Tura casing stones were laid first. Remember that they had been cut side by side at the quarry and numbered. So they only had to be laid according to their numbers, rather like the pieces of a model, to construct a perfect casing right from the start. There was therefore no need for facing at the end of construction, which represented a great saving of time, especially when we consider there were 84,000 square meters of casing. When this was done, there was an enclosed working area into which the cut blocks of local limestone were brought by way of the external pyramid ramp for the construction of a second belt about 20 meters thick. This structure gave the pyramid its solidity. It's these stones that can be seen today, the Tura limestone having been removed in the Middle Ages for the construction of the monuments of Cairo. Once this finely finished structure was in place, there was no longer any need for such fine construction. Speed was of the essence. The center of the pyramid was thus filled with very roughly hewn stones, blocked with quarry rubble, and often a little mortar. There was one exception, however. This sort of finely finished peninsula visible in the middle of the infill. This was to serve as the foundations on which all the internal works, as the Grand Gallery and the King's Chamber, would be constructed. It was out of the question to build such structures without solid foundations. The terrain having a slight slope, they kept a section of bedrock about 7 meters high. This light patch that we can see at the top right inside the monument. Only the bases of the casing stones were leveled at the start of construction. The pyramid was thus anchored solidly on this natural foundation. In doing so, they used almost 400,000 tons of limestone that was already on site. The Egyptians thus continued to construct the pyramid in successive courses from level 7 to level 43, that is, from 7 meters to 43 meters high. At level 43, the volume constructed represents about 2/3 of the volume of the structure. The Egyptians supplied the worksite with local limestone using the external ramp and transported the casing stones of Tura limestone up the internal ramp. In about the 14th year of the king's reign, the construction having progressed well, the pyramid reached a height of 43 meters. The construction from the inside, that is, inside out, left the rest of the Giza plateau totally free. This was important because the other monuments of the funerary complex could be constructed independently. We can see the beginning of the construction of the upper and lower temples and the royal causeway. Moreover, as deaths occurred in the family and those close to the king, mastabas were constructed nearby to receive the deceased, and even small pyramids for the queen mother and the king's wives. The Great Pyramid slowly became the center of a veritable necropolis. On reaching the base of the king's chamber at 43 meters, the construction process needed to evolve. With the Great Pyramid, there were 3 challenges in one monument: the volume, the king's chamber, and the height. 14 years had been spent successfully tackling the volume challenge. Now came the second challenge. The choice of a flat ceiling for the king's chamber obliged the Egyptians to use granite, the only material strong enough to span the 5-meter width of the chamber. There were also 4 further ceilings above the first before the chamber was covered with a roof in an inverted V-shape consisting of limestone rafters. The room therefore reached 21 meters in height in stages, from level 43 to level 64, which was unique in the architecture of Egyptian pyramids. Here we see the floor of the chamber, made from heavy slabs, and the northern wall, all of granite. Close to the southern face we can see the rafters and several beams on a storage area. It would be necessary to lift 50 granite beams and 22 limestone rafters to level 43, and then position them in their final location. That was the big challenge of the king's chamber. How did they transport them to this height? To hoist monoliths weighing up to 63 tons to this level would need several hundred men. Quite simply, it would have been impossible to coordinate so many workers, and it would have required a lot of room for them to pull it up. Now, because of the shape of the pyramid, the higher one climbed, the less space there was. They had to think of another solution. All the granite beams extracted by the Aswan quarrymen arrived at the port, where they were stored. The beam was borne on a sled that rolled forward on logs. Past masters in balancing games, the Egyptians invented a device to reduce the effort required by the workers to move the monoliths. It was a counterweight, similar to that of an elevator. At the end of the port ramp, they dug a trench into which a counterweight descended. Linked by lengths of rope to a sled on which the beam was loaded ready for transport by rolling on logs, this counterweight essentially supplied the tractive force. The depth of the trench was calculated so that, once the counterweight reached the bottom, the beam moved a distance equal to one rope length. They just had to block the beam, remove this length, lift up the counterweight, reattach the ropes, and start the operation over again. The port ramp would later be used as the foundation for the royal causeway of Khafre's pyramid. Signs of this counterweight and the trench can be seen in the access corridor to the Khafre's funeral chamber. The beam was transported in this way to the foot of the pyramid's external ramp. It was then rotated a quarter turn, still on wooden logs. The beam was hauled by a second counterweight that raised it on the external ramp to the 43-meter level, where it was stored, waiting to be used. The second counterweight travelled in a structure built at the same time as the pyramid, in its heart, the Grand Gallery. Here we can see the ropes descending into the Grand Gallery, which remained partly in the open air. It's been suggested that this structure had a religious, funerary, or even symbolic role. It's alleged to have served for the funeral of Khufu, or even to have symbolized a ramp for the king's ascension to the gods. If such were the case, one would expect to see inscriptions or ornamentations indicating such a purpose. But there is not one. The Grand Gallery's purpose was exclusively as an aid to construction. The beam was thus hoisted to the pyramid's working level, 43 meters above the ground, by means of this second counterweight. Some months had passed, and the granite beams and the limestone rafters required for the construction of the king's chamber were now all arranged in the new storage area on level 43, ready for the next step. The external ramp was now at its maximum height. The construction of the king's chamber had begun with the laying of the floor. Now the walls and ceilings needed to be built. There again, the counterweight in the Grand Gallery played a major role in helping to hoist the beams from the storage area to their final position. The Egyptians thus constructed the 5 successive ceilings of the king's chamber, a project that was unique in Egyptian architecture. For this, a cross-sectional view will be more practical. We have made all the surrounding stones transparent to make the important elements stand out. Moving around in the Grand Gallery, we see the counterweight, a wooden sled loaded with several blocks of granite, weighing around 25 tons in total. When the counterweight descended, the beam on its platform at the opposite end rose to the desired height. To limit friction, the Egyptians used a train of cedar logs kept in alignment by a wooden structure which travelled up the steep slope of the Grand Gallery. The counterweight frame moved on these rollers, which rotated as it passed. With the assistance of the counterweight, only an estimated 180 workers at the most would have been needed to hoist the granite beams, including the heaviest one of 63 tons. An old bas-relief illustrates the transportation of a statue of more than 60 tons with a similar number of workers. So the idea appears quite feasible, historically as well as mechanically. When the granite beam arrived at its destination, the counterweight was at the bottom position in the Grand Gallery. It had to be lifted back up for a new lifting operation. The beam-carrying platform was then ballasted with around 15 small stones of 2.5 tons, easy to move, a sufficient load to reset the Grand Gallery counterweight. The platform thus became the counterweight's counterweight. Once the rafters were in position, the counterweight was dismantled and the 3 main ballast stones were lowered to the bottom of the ascending passageway to prevent access by robbers. For this reason, they're called ceiling blocks. There are many signs to support the use of the Grand Gallery as the counterweight slide path. Let's see now how the Egyptians constructed the ceilings of the king's chamber. In about the 16th year of his reign, the 3rd ceiling was reached, of a final total of 5. From the storage area on level 43, the beams were hoisted to their final height by use of the counterweight. They were then hauled into place and installed side by side to form this ceiling. Each new ceiling in the king's chamber was constructed at the same time as the course of the pyramid at the corresponding height. In this way, the pyramid's construction continued to advance at the same time as the king's chamber. The Egyptians continued delivering the blocks of local limestone by the external ramp and the casing stones by the internal ramp. This internal ramp will emerge in the southwestern corner and continues from the southeastern corner. Between the two, the teams pulled the Tura stones horizontally along the edge of the storage area, which enabled them to continue using the exterior ramp. There is nevertheless one oddity during the whole length of construction of the king's chamber. The need for a storage platform at level 43 caused the temporary stoppage in the construction of the internal ramp close to the southern face. The storage platform at level 43 remained in service until the end of construction of the king's chamber. The goal was to avoid impeding the massive transportation of stones that was still in progress on the external ramp in order to supply the pyramid's construction. The external ramp reached its maximum height at the level of the storage area. The Egyptians extended it with a ramp in an open-air trench along which we can now follow this stone. This trench climbed within the body of the pyramid, making a quarter turn in the opposite direction to that of the internal ramp. Obviously, the spiral tightened as it climbed. At a height of nearly 70 meters, this ramp had to end. Nevertheless, using this ramp and the external one, the Egyptians constructed 85% of the total volume. At this stage, two construction phases were finished, the volume and the king's chamber. Now was the time to move to the third and final challenge, the height. First, let's summarize. First, the storage area for the beams and rafters at level 43 at the top of the external ramp, which continued in a spiraling trench. At level 70, the rafters were installed to finish the king's chamber. The spiral trench and the storage platform at level 43 were filled in and leveled. The two openings of the internal ramp behind the southern face were connected by a horizontal segment. This is thus the only segment of the internal ramp that does not rise with a gentle slope of 7%. This was the price paid for being able to use the external ramp to the maximum by extending it in a trench. It was worth the penalty, since there only remained 15% of the volume to construct. 15% of the volume, yes, but still a little over half the height. The question was now how to reach the summit and finish the pyramid. The answer? The internal ramp. At a height of 70 meters, space was limited, and the blocks were now a lot smaller, from 500 kilos to 2 tons, and so could pass through this rather narrow tunnel. We should also remember that the external ramp, whose role had come to an end, was constructed of quality limestone. Therefore, it represented a reserve of materials that were ready to use and, what's more, ideally placed. The Egyptians now dismantled this external ramp, recut the stones, and raised them via the internal ramp from its entrance at the base of the pyramid. Two types of stone would travel through the internal ramp from now on: the Tura casing stones and the recycled stones from the external ramp. We can see in the images how the external ramp diminished while the Egyptians finished the pyramid. This is the reason that no trace of the external ramp has ever been found on the Giza Plateau. It is, right before our eyes, recycled in the upper part of the pyramid. A last clever move by the Egyptians. Proof, as if it were needed, of their great intelligence and careful planning of the construction of the Great Pyramid. But let's now follow this block up the internal ramp. We can see that the workers had just one thing to do: pull the stone in a straight line up the gentle 7% slope. The ramp, as in the segment where we are located, was lit by oil lamps. Open at both ends, it was ventilated naturally, which provided proper working conditions. When it reached the end of a rectilinear segment, the block was rotated a quarter turn, again using a system of counterweights. This system was derived from the ancient shaduf, or counterpoise lift, that the Egyptians used to draw water from the Nile. Already perfected at the time, this system enabled a single man to raise the stone and its sled. The whole thing was then turned 90 degrees to line it up with the new section, then laid down again, ready to be taken care of by another team of workers who transported it up to the next point of rotation. The corner chamber in which we've just seen the block being rotated was located behind a notch on the northeastern ridge of the pyramid. Explored by the American Egyptologist Bob Breyer, it was completely recreated. Thus the block passed through the internal ramp and was rotated at each corner in a chamber similar to Bob's room. The workers we've just seen depositing the block to be rotated then returned to the start of the flight to get another. They used this ladder and went back down using the upper level of the internal ramp, taking an empty sled with them, which had been left by a team from the following section of ramp. The Meidum Pyramid proves that the Egyptians know how to deal with an intermediate floor in a structure covered by cobbled vault. This two-level ramp meant that a returning team with an empty sled did not impede the ones that were ascending with a new stone, so that no construction time was lost. Here we follow the journey of the workers and take the upper level of the ramp back down. Now here we are outside. The exit of the ramp is right beside the entrance. Here are two photographs, one recent and the other older, where the lighting reveals what could be the entrance and exit of the internal ramp. You can clearly see a rectangular zone where the stones are not installed in the same way as elsewhere, and the shape revealed seems to correspond to the supposed ramp openings. Moreover, a French mission conducted in 1986 under the aegis of the EDF Foundation studied the pyramid using microgravimetry. This technique serves to detect voids and is often used by EDF to check for the absence of underground cavities, for example at locations where high voltage pylons will be erected. The technique was used here to look for an unknown room. Here we can see a plan view of the pyramid with the internal ramp proposed by Jean-Pierre Houdin superimposed on the image of the microgravimetric readings from the 1986 mission. The green zones represent areas of very low density in comparison with the red ones, in other words, potential voids. One notices a disconcerting resemblance to the drawing of the internal ramp. The yellow segment corresponds to the horizontal segment of the ramp at level 43, and the circle at the top in the right-hand corner to the room explored by Bob Breyer, known as Bob's room. In this 3D view, the matching of the microgravimetric image with the internal ramp of the theory is even more striking. This series of corroborating indicators was encouraging, but only on-site investigations dedicated to the location of the internal ramp would definitively establish the validity of Jean-Pierre Houdin's theory. He has always favored non-destructive techniques. Interfering with the pyramid would be out of the question. Jean-Pierre first envisaged microgravimetry or surface radars. Then teams simulated the effect of the sun on the model of the pyramid without the internal ramp and then with the ramp. These simulations showed patterns of sufficient temperature differences to make it a good candidate for infrared thermography. Moreover, a team from Laval University in Quebec City is working to follow this promising trail. The pyramid was now finished,